Today we're going to spend some time digging through some of the architectural decisions that AMD made for its RX 7900 XTX and RX 7900 XT GPUs using the new RDNA3 architecture. In this video, we'll be going over some of the finer details of how these cores actually work, how they've been refined, and critically, we're going to use some of this information to start looking at what previous weak points AMD might have addressed and what new weak points it might have created. Let's get started. Before that, this video is brought to you by Crucial and its DDR5 memory for Intel or AMD Ryzen CPUs. Crucial makes DDR5 kits that are deployable in Ryzen 6000 laptop systems and in Ryzen 7000 systems or Intel Alder Lake, including both budget-oriented and performance-based memory modules. If you're building a new system, click the link in the description below to learn about Crucial DDR5 memory. Okay, so this is an architecture video. That means we're going to be going over some block diagrams and talking about things like terminology and changes to the actual inner workings of the GPU leading up to the 7900 XTX launch. We like to try and put these videos together. We did one for Ampere also because it helps everyone just sort of understand what is that's actually going on as much as we can. But frankly, the level of detail that AMD and NVIDIA provide on these architecture deep dives is way over the head of anyone who's not an architect. I'm not an architect, for example, but we understand a good chunk of it, and that's what we're going to help you break down and understand as well. So the actual GPU in the 700 XTX or the 700 XT, that is called Navi 31. You're going to see Navi 31 used interchangeably with these occasionally. It's built on the RDNA3 architecture, and there will be non-Navi 31 GPUs that are also on RDNA3 architecture, just they'll come out later. This is moving on from RDNA2, predictably, and the 6000 series previously. We're going to pop some B-roll up from when we went to the AMD event, and just as a reminder, the large die in the center, that is the GCD, or the graphics compute die, and the dies that are surrounding it are the MCDs, so those are the memory cache dies. And with this layout, AMD hasn't fully broken up basically the GPU shader cluster into multiple chiplets. Instead, they've gone with one pseudo-monolithic GCD plus the interconnects that bridge it to the MCDs. So that's what we're going to be talking about today is this layout. If we could zoom into the AMD graphics compute die, that big block in between the memory and the cache dies, we'd see this layout of the units within the GCD. This type of diagram is known as a block diagram, and they are awesome. They're really good for illustrating the composition of silicon underneath the shiny diffusion barrier. The 5 nanometer GCD is the large block in the middle, and then the 6 flanking are 6 nanometer smaller rectangles attached via interconnect for the memory cache dies, and we'll come back to those. Internally, the GCD is comprised of a mixture of shader engines, Infinity Fabric, and other engines like multimedia or PCIe. These are used somewhat modularly, as with any architecture, to build each class of GPU. The shader engine count and the cache capacity, the latter illustrated by all the L2 markers and the various L1 markers, will get cut down as AMD launches more GPUs. You might see some of these shader engines disappear in future mid-range products, for example. You could also see the MCDs modularly disappear. For example, the already announced 7900 XT, that's going to go down to 5 MCDs, or 5 of the memory cache dies, from 6. So where you see 6 surrounding it, it's going to deactivate one of those, and that one that's deactivated will become dummy silicon. We don't know if it's going to be the same one every time, or maybe they'll do it based on the quality of the chip or something, or the bin, or where the defects are. Either way, one of those will be fake on the 7900 XT non-second X. Maximally, there are 6 shader engines for the GCD here. Each of the shader engines compartmentalizes a group of 8 dual compute units. It also has 2 blocks of L1 cache and then the rasterizers. So that means a maximum of 48 dual compute units because 6 shader engines times 8 dual compute units per shader engine. So you get 48. And then each of those, the name dual, tells you that there's 2 of the traditional compute units in them, or the CUs. So you end up with 96 CUs. This maps back to terminology AMD's been using for a long time now, and AMD is still running 64 stream processors per CU. So simple math, you do 64 times 96, you end up with 6,144 for stream processors for the highest end AMD GPU on RDNA3, and then they'll cut that down. So as those different blocks disappear from the block diagram, they go down to lower end stuff. obviously the numbers will decrease in all of these three categories. So, and just for the record again, these stream processors can't be compared like for like with NVIDIA's CUDA cores, just like the CUs can't be compared like to like for the SMs from NVIDIA. So the architecture here is vastly different in some ways that are critical to them not being comparable just on paper. At least not this kind of paper. You could compare it on paper if maybe you're an architect or a lead engineer at NVIDIA or AMD, but we're not going to be comparing it on paper. We're going to wait till we can run them because it's easier that way. Now, within these units, key things to look out for include further improvements to rasterization and primitive processing. Primitives come up a lot with AMD's architecture discussions because of AMD's Mike Mantor, who worked on Mantle, if you remember that, which led into eventually Vulkan. Mike Mantor has been there a long time, and he really likes to talk about primitives, which is cool because it gets into the graphics technology of what the GPU is actually processing. So you have some better understanding for what it is the thing is doing, what's being represented by all of the math. And primitives would be typically triangles. Could also be other simple shapes, but basically what you're talking about is triangles that comprise ultimately a 3D image after they've kind of been processed through and gone through culling and things like that. So primitives or triangles are what construct basically all of computer graphics. And one of the things AMD has done with RDNA3 is add a small accelerator. And this accelerator improves the speed of CPU draw calls as they get processed by the GPU. So AMD here claims an uplift of 50%, moving to 12 primitives per clock through culling. And it also noted that hardware culling had been improved this time around by 2x for each unit for the primitives and the vertices. So culling here refers to the act of getting rid of unnecessary primitives, unnecessary triangles, unnecessary geometry, polygons, things like that in the scene. So for example, if an object is partially occluded by some other object, and you don't need all of the, people are getting real nervous right now, and you don't need all of the triangles that create that object. Actually, this is a good example over here. If we take one of the coasters and we occlude the GPU from the view frustum, if that's where the camera is right now, then what we can do on the GPU hardware side, or potentially on the game engine side, or a mixture of both most likely, is work through to cull the triangles that are not visible to the camera and will not be useful for purposes of presenting a scene for the player to look at. And you get into some complexity with things like, well, okay, but what if those triangles that are unseen have some impact elsewhere, like maybe a shadow that's being cast, or ambient occlusion, global illumination, things like that. And there are answers for each of those, but it's a different topic entirely. So in this instance, the GPU does play a big role in efficiency for culling and getting rid of unnecessary geometry so that it's not burning cycles and resources, rendering the part of the card on the table here that you currently can't see. It might instead render this coaster, which even in the actual world here, if we were to pretend this is 3D space in software or something, the coaster would take far fewer triangles to create than all of the fins that are being hidden on the GPU. So you're saving potentially thousands or tens of thousands of polys that could be burned on something else in the scene instead. So AMD has done some work here to improve the culling process. It also improved the pixel pipe with a 50% increase in rasterized primitives and in pixels per clock, which should help with higher resolutions. AMD also added out-of-order exports from the shader, and it's been doing a lot of work with out-of-order execution this time around. And out-of-order processing here is really useful, just like it is in CPUs or anywhere else in computing, because once you kick off the process, you can start the next one in parallel, even while that first one is still running, so they can kind of run somewhat in tandem. So AMD has worked on these aspects. We'd also expect to see a lot of these upgrades result in increased rasterization performance, which we already know from AMD's preliminary first-party benchmarks is going to be something that is realized in the numbers. What we don't know is how much ground it might gain in 4K compared to its 1080p and 1440p advantages it had previously. So previously, you could look at the 6000 series one of two ways. Either it was particularly good at 1440p and below, or it was a little bit bad at 4K just relative to its 1440 and 1080p performance. But in either instance, what we're going to be looking for is, has that changed at all behaviorally, or is this maybe still inherent to RDNA even if it's version 3 now? AMD also spoke of improvements to integer 8 and FP16 processing, but those are less relevant for gaming use cases, which are still primarily FP32. We can go one layer deeper though. If we could zoom in to one of the dual compute units that we talked about earlier, this is what we'd see. Each compute unit is now paired with another, a departure from previous designs. The two compute units are joined by schedulers and contain scalar and vector units, including the FP32 and the int processing capabilities. These units share access to the L0 cache. That's the fastest memory on the GPU. It's now at 32 kilobytes, but you'd multiply that depending on which die configuration it is. They also share access to the ray accelerators, the texture filters, and the load and store functionality. This is where AMD shared some additional insight as to one of its own self-diagnosed shortcomings of RDNA2. AMD noted that in RDNA2 they were generating too many quads or polygons basically, and they were losing efficiency there. So in RDNA3, AMD has moved to what it calls a 2-level scheduler, which it uses to rapidly determine the 3 necessary or most necessary quads to generate the desired data, to cut down on unnecessary quads or polys that are being generated. So AMD gave one example where this singular improvement contributed to a 40% decrease in unnecessary quad processing, but it also stated that the deltas will be all over the place, so it's not always going to be a number that's necessarily that big. And it also said that this can help with texture processing as well. AMD's also been talking about its out-of-order opaque exports. This allows for better load path optimization that will improve rasterization and improve how effective the shaders are when rasterizing. Up next, AMD's cache system, at least as we understand it now, from AMD directly, and also as we understand it on the team, because again, the architectural deep dives are great as a learning resource, but there are many parts of that go kind of beyond the scope of what we know. But we've done our best with it. So cache is one of the biggest uplifts with RDNA3, where anytime a GPU or a CPU needs to hit the cache for something, it's saving time versus going out to some other form of memory. So for a CPU, your only other option really, other than with the newest stuff where they're starting to explore HBM, is going to be to go to system memory. It's slow, it's much physically farther away, and also you're stuck on different interconnects or bandwidth limitations that may impede the process of getting to that data that you want, rather than pulling it straight out of cache, which is basically local residency to the processing that's happening on the CPU itself. So for GPUs, you have one other step in there. You can go to GPU memory, or in the absolute worst case, you go down the PCIe interface, through the PCIe connections to the CPU and over to system memory eventually to fetch that information, pull it back through the PCIe interface, back into the GPU, and that's a slow process. So cache, none of this is new, but this is a simplified view of why cache is so desirable in larger quantities. But every piece of cache costs not only money, but also die space. So when these companies, one of the reasons they don't just throw more cache on there, even if you ignore cost as an actual money, is because of die area cost. That is space that they could have potentially used for something else that maybe would have been more important. Here's the new cache system. We'll start at the right of the image. You can see GDDR6 is off the page, pushed to the right, and GDDR6 is connected to the 96 megabytes of Infinity cache via a 384-bit wide bus that operates at nearly 1 terabyte per second. The RX 6900 XT used a 256-bit bus, so that alone is a 50% increase in bus width, but there's more to it than that. And remember also that not all RDNA3 GPUs will be 384 bits wide, because even just with the 7900 XT, we already know we're killing one of those MCDs, and you're cutting down to 5, and naturally as they cut down MCDs and they cut down the memory controllers, the bus width will shrink. But it might not actually be beneficial to have all that width if you're starting to also axe shaders. The L2 cache is connected to L3 via its own link, with L2 at 6 megabytes and accessible 16 ways. That then talks to 12 L1 blocks. Here you can see the interconnect speed increases as compared to L2 to L3, showing the increasing value of lower level cache that's closer to the shaders doing the math. The L1 is 256 kilobytes per array, so that's 3 megabytes total. In total, that's a 300% increase generationally per AMD's own numbers with its better GPUs. Finally, L0 has increased by 2x, now at a maximum of 3 megabytes total as well. AMD noted that these increases allowed a reduction of overall internal bandwidth, which gives them more space for other hardware. Now, just briefly, as for ray tracing, which most of this we'll save for actual performance testing, AMD noted that its ray tracing performance is up as much as 80%, and a lot of that gain this generation, this is generationally best to best, is due to advances in logic, like we were talking earlier about culling. Culling is not limited to just triangles, it can also be used for rays. So one of the things they're doing is culling ray calculations earlier when it is determined that those ray calculations are not relevant to the end result that is being rendered. So it can save some of the processing overhead there. And also it has better sorting algorithms for different types of rays. One of the things we talked about in our interview with AMD's Sam Nafziger about the architecture, the interconnects, and the challenges of moving to chiplet for GPUs. It's on the channel if you want to check it out, and you should. One of the things we talked about was how it's not necessarily as easy as sort of copy-pasting the concepts from CPUs into GPUs and just dicing up the block diagram somewhere and moving forward. So one of the limitations here is that on CPUs, there are hundreds of interconnects that are required to go between the CCDs, so that'd be the core complex dies with the actual cores on them, and the I/O with the I/O on it. You come here for this kind of depth. The I/O die has I/O. So with hundreds of interconnects, the difference from GCDs and MCDs, difference between GPUs and CPUs here, is that with GPUs you're dealing with tens of thousands of wires, basically interconnects, and each one of those relies on actual copper traces to make the connection. That's a lot of density, and when those are part of the in-silicon design, it's, at least as Nafziger explained it to us, relatively simple, but joining two discrete dies with another material is difficult. Traditional methods of interconnect via an organic substrate just aren't physically dense enough to meet the bandwidth demands of a chiplet GPU design. AMD's way to address this is by modifying a really compact form of interconnect, originally designed for mobile phones, to meet the high performance requirements of a GPU. That's the fan-out design we talked about with Nafziger previously. The company is calling this an Infinity Link, and it operates at 9.2 gigabits per second. This approach scales all the way up to a massive 5.3 terabytes per second, given enough of those individual links. In this shot, we can see the large difference in density between these interconnect or fan-out technologies. Shrinking these links down has also enabled AMD some pretty impressive power savings, according to them at least, on the link itself. It requires up to 80% less energy per bit versus organic substrate links. That said, the interconnect only accounts for a small part of overall package power. However, using interconnects to link dies incurs a memory latency penalty versus monolithic. Clock for clock, the new Navi 31 design has higher latency than Navi 21. AMD is able to combat this with frequency boosts of 43% for the Infinity Fabric and 18% for the game clock. This results in matching or slightly beating Navi 21's latency. When all of this is added together, the end result of the chiplet and interconnect approach is a 20% relative increase in silicon utilization. Time to cover the decision to move to chiplets in more depth. Some of this we talked about with Sam Nafziger in that interview, so those bits will be repeat information, but also some of it's new, and we've just kind of merged them together to create a fuller picture, because we only had about 15 minutes before the cleaning crew kicked us out of the conference room we were in. So the RX 7000 series obviously is the first consumer video card that is using chiplets, and that's a big move on its own. We already covered that basic fact, but fundamentally this is an effort to keep cost in check. The more advanced silicon process nodes get, the more expensive they are to use. That's okay if a lot of performance comes along with it, but certain aspects of CPUs and GPUs don't scale down to smaller nodes very well. Analog input and output designs have essentially stopped scaling, and memory is gaining less benefit from node shrinks as well. Logic, however, like the actual shaders that we just talked about in a GPU core or the cores in a CPU CCX or CCD for AMD designs, that's still benefiting from the more advanced nodes in drastic ways, and it's important to leverage as much of that node die area as possible in these designs to benefit the part of the technology that sees the most gain. If, as in this case, I/O and memory have slowed down on what they gain from the absolute newest leading technology or process node, then it makes sense to just pull them off of that, put them onto something technically a little bit older, and allocate all the most expensive stuff to the most important part of your product. Production on the latest nodes represents a higher cost per millimeter squared than ever, at a higher rate of increase than previous shrinks as well. That's the driver behind chiplets. It's just going to become impossible to make affordable products with silicon if we keep cramming them in on monolithic designs that are massive. AMD has been using this approach on its Zen CPUs since the 3000 series to great effect. The I/O die is on a larger node than the CCDs. This makes the whole CPU less expensive to produce, as AMD not only gets to use the cheaper silicon where it makes sense, but also reduces the physical size of a single die. Silicon manufacturing also gives better yields on smaller chips, and higher yields means less wasted silicon, resulting in lower cost there as well, and that gets passed on to consumers. This image is pretty interesting. It's one that we talked about before, so it'll be brief here. AMD ran a cost analysis on hypothetical monolithic versions of its Ryzen CPUs and concluded that a 16-core CPU would cost over 2 times as much as the chiplet approach. Further, an 8-core monolithic CPU would cost almost as much to produce as a 16-core made with chiplets. The larger you push die size, the more the yields go down and the cost skyrockets. We can see from this diagram that on the previous Navi 21 design, the graphics engine is almost surrounded by cache and memory interfaces. Both things that we just talked about don't benefit very much from advanced silicon. That's where AMD saw the opportunity to literally sever and separate these areas of the design from the main chip. AMD is using 5 nanometers for the GCD, and then it's using older process nodes that are less advanced for the MCDs. Moving on to the physical design of the cards now. So we're past the silicon, we're on to the product level stuff. We already showed the 7900 XTX and XT and some footage when we were at the event previously, but we also got some details that we haven't been able to share until now. So one of them is this render of the 7900 XTX PCB. AMD provided this, and even though it's not a real photo, it's supposed to be accurate. Starting from the left edge, the card has 2 DisplayPort 2.1 ports, 1 HDMI 2.1A, and 1 USB Type-C. The Type-C is something that we saw physically on the cards as well when we were at the event, and it's also something that we saw in the RTX 2000 series, but not in many other places. This can be useful for things like VR or the rare monitor that uses DisplayPort over Type-C, but otherwise it's just a regular high-speed USB port where a normal monitor connector could be. AMD also points out low PCIe slot peak currents. Apparently, AMD is still haunted by the specter of the RX 480 PCIe slot power scandal, in which maybe one damaged motherboard ever serviced. Outside the package are 12 VRAM modules, totaling 24 gigabytes of GDDR6. The cut-down 7900 XT will only have 20 gigabytes, so 2 of these chips will be missing. We just don't know which ones or if they'll even be consistent. Moving outward, there are VRM components to the left and right of the die and the memory area, making for a total 20 or so phases, at least based on this render. We don't know how many will be dedicated to vCore versus vMem, but there are more than enough present to go beyond diminishing returns with a competent design, depending on the FETs that they use. One more interesting note here is that AMD is using a very thick 14-layer PCB for its reference model cards, which is among the densest we've seen. NVIDIA's up there as well now. And it's necessary for extremely compact high-performance designs like, say, the 4090. The 7900 XTX doesn't run the weird sort of cut-shaped PCB at the shorter size, so there's other benefits too, some of them thermal, for example, and some of them just general build quality. But either way, they've gone to a thicker PCB this time. Finally, power is delivered to the card via 2 standard PCIe 8-pin power connectors. We talked about this before, but there were rumors that AMD had apparently switched off the 12-volt high power 12 plus 4-pin option when NVIDIA had its first issues with adapter cables. And just once again, that's not how any of this works. That is not anywhere close to enough time to make that kind of change on a board this late in the process. So that's something that AMD settled on, those 2 8-pins. a long time ago, and most of it has to do with just simply not needing the amount of power density that a 12-pin can handle, which is like 600 watts, because AMD is just running its cards below 600 watts. As for AMD bragging on Twitter about it, like you see here, we'd like to remind AMD that it was one of the signatories that contributed to and signed off on the ratification of the 12-volt high power connector as submitted to PCI SIG. So while it's cute that AMD is using this for marketing, we'd prefer to see them actually market something that they've done that's really cool or different, like any of the things we've talked about so far. Anyway, moving on to the exploded view, we see a bit more detail on the cooler design. AMD calls out that it's using a new dispensed TIM on the memory, which we assume means the same sort of putty type found on the 40 series or that sort of canvasy type interface. The heatsink uses a vapor chamber. It's not actually visible here, but it's becoming increasingly common on high power cards. And AMD took a few more shots at NVIDIA, starting by devoting a whole slide and part of another slide to the fact that no dongle is required for power. The standard 8-pin, it's a good connector. It has years of service, and we know it's proven to be reliable, easy to use. It has a really resilient mechanism. It makes a clear click when you lock it into place. We just don't think it's worth marketing it because it's not something that AMD or NVIDIA really specialize in. On to driver and software updates. AMD has been putting a lot of work into its Radeon drivers and software, and it's come a long way from the days of Crimson. So there's performance features like AMD Boost, there's also super resolution, there is FSR, there's anti-lag. Some of these we've tested in detail, some of them we've kind of skipped over just because of somebody like Radeon Chill, for example, we never really worked on. Now, these features have been around for a long time at this point, some of them anyway, but AMD told us that since they were developed as separate technologies, one of the challenges they've run into is that a lot of people are either not aware that they have all of them, or they don't check to see if the games they're playing support them. And so AMD now wants to make this simpler. That's where it introduced its Hyper RX solution. Hyper RX in itself is not a new technology like these. It instead is a toggle that turns all of these performance tools on simultaneously as long as the game supports them. But the fact that it's just something you toggle on or off, it does the rest of the work thinking about if the game supports them. And that last part is important because historically, anytime the game developer is required to make special accommodations for a feature, adoption rate is low. At the time this information was shared with us, 40 to 50 games supported Boost and 30 to 40 supported anti-lag. That's better than Crossfire SLI, especially, well, today anyway, but it's still low in the grand scheme of things. AMD told us that in the best case scenario, Hyper RX was able to give an 85% uplift in frame rate in Dying Light 2. When asked for sort of a breakdown of how this 85% was gained, AMD noted that most of that was from super resolution, although it also had some latency improvements in the same game. So for Dying Light 2, they saw it move from 30 milliseconds to 11 milliseconds from end-to-end latency. AMD also pitched this pretty strongly as a better solution to DLSS 3 because with DLSS 3, you're using frame generation, which can technically actually increase the latency. So AMD was pushing that angle as well. Now, in practicality, the better approach is going to be situational here, where if you're playing a competitive game, you're probably going to want the lower latency versus a smoother experience for generated frames. If you're playing something casual or slow-paced, you might prefer smoother play with higher latency. That's just going to come down to preferences. And now on some of the other technologies, so creators came into the focus again, where AMD is bringing a few features focused on streaming. It talked about AV1 encoding. It talked about audio noise suppression coming in from AMD's built-in streaming and recording tools. And these are the same types of advancements we've seen made over the years from actually both vendors at this point, NVIDIA most recently, and to some extent Intel as well. But it's AMD's turn to talk about implementing them. They're all good things, just we've kind of talked them to death at this point. Now on to the AMD ecosystem stuff. AMD's been making CPUs and GPUs for a long time. They're starting to lean more into the, hey, you should use our CPU with our GPU, and you get these technologies together. According to AMD, today's PC problem, their terminology, is that there are computer parts, in fact, that are not made by AMD. And that wasn't a problem when AMD partnered with Intel for 8th gen laptops, or when AMD partnered with NVIDIA, with EPYC. But basically, if AMD makes money, it's okay, and if AMD doesn't make money, it's not okay, so you should buy Ryzen and Radeon together. And that's all fine. Intel's done this exact same thing where they've talked about, I don't remember if it was AMD or Intel using the phrase better together, but they've both effectively said that. Actually, Intel said it with the original visual BIOS, they called it, when UEFI was still starting to kind of get to rolling out. Anyway, everybody's made this point at some point. And what it is for today is that smart access memory is the main one AMD is talking about, where SAM isn't new, but the point here is that AMD is claiming that SAM, or smart access memory, is more effective than just straight rebar. SAM is sort of built on top of rebar, but it claims to gain on average 8 to 15% uplift in SAM via AMD, whereas rebar via AMD sees 5% uplift maximally. Now, in our own testing using resizable bar, the benefit of this kind of thing varies from game to game, and we'd have to really expand our SAM testing across just an unreasonable amount of games to determine if it's better or not on average. So for now, we'll just take their word for it and move on. One thing that's actually new is Smart Access Video, or SAV. It's a technology that allows software to leverage the couple of GPU cores inside of a Ryzen APU or a Zen 4 CPU at the same time as a Radeon GPU for video transcoding. This is actually really cool, speaking as people who work in video, because it's one of the few things that in the past made Intel CPUs actually bizarrely compelling for working on videos, not anything else except for the IGP. So AMD is claiming up to a 30% boost with SAV on. It's a cool idea to be able to use all the processing power available to you for tasks like Adobe Premiere rendering. It'll just come down to how much of an uplift you can get in the real world and what software is supported. And finally, the last thing we learned from AMD's presentations was more about AMD's Advantage program. AMD Advantage is basically, but not really, a stamp of approval from AMD, although when explicitly asked, they said it's not a stamp of approval, but it is. When the laptop vendor historically puts together a design that AMD says, yep, you can call this AMD Advantage. Now, it's not licensed. As far as AMD says, there's no MDF, Exchange of Marketing Development Fund. There's no validation cost. So it's not supposed to be a money-changing hands thing. They're basically saying this device is built to whatever our standards are at this particular time. And that's fine. Multiple companies have done stuff like this. Now, in this instance, AMD's introducing Advantage to desktops. And Advantage desktops specifically use Ryzen 7000 CPUs. They will use Radeon 7000 GPUs. And then there's a couple of other requirements. Those include a premium case. And apparently the delineation there for premium is toolless. Sort of terrifying here, but technically AMD Alienware R13s are kind of toolless. So that aspect, not a selling point. They also require a GPU retention mechanism. This is actually a good thing for shipping a whole computer that's pre-built. They require liquid cooling on the CPU. If that goes down to 120 mil, then it doesn't really mean much. It requires a 2 terabyte or larger NVMe SSD, and for some reason, at least 32 gigabytes of RAM. The slide in the presentation also implies that Expo will be required, which would be awesome, because this is one of the biggest things we've struggled with pre-built manufacturers, where they don't use the higher memory speeds that are available to them. However, when we asked AMD at the event if Expo would be required, the answer was not at this time. So we're a little bit confused about what any of that means and when it will be required, since the slide seemed to imply it. But anyway, in addition to the latest hardware, the Advantage program also calls for, quote, proper cooling at less than or equal to 42 decibels, although we'd have to really look at their methodology to know what any of that means. AMD wasn't explicit with what it means by proper, but it told us that we make sure that we require a cooler or cooling solution that gives them the thermal headroom for the CPU to go to its maximum potential. Considering our track record with reviewing pre-builts, we look forward to AMD Advantage desktops. If they actually fix this problem, then they would be some of the best performers that we've looked at in a long time, so we'll be buying some. Ultimately, the system integrators are going to charge some kind of markup to call it AMD Advantage, even though there's technically no exchange of money between AMD and the system integrator, because from the system integrator's viewpoint, they are making something that's higher quality and therefore should cost more. From our viewpoint, the system integrator is making something at baseline required quality, but they're going to charge more. So, but that's not an AMD problem. That's a system integrator problem. That's it for this one, though. Hopefully that helps you get fully recapped on all the stuff that happened at the AMD event. The architecture stuff, it's always really fun to go through it. We work pretty hard to understand as much of it as we can, but just realistically, with all of you, there's a lot of slides in there that don't mean a whole lot to us because it starts getting into really specific functions like FMA and stuff like fuse, multiply, add, and all the different aspects of CPU and GPU processing. So we've broken it down as much as we can for you, and hopefully that helps out. Check back for the reviews when we get the cards in. Subscribe for more. Go to store.gamersnexus.net or patreon.com/gamersnexus. Helps out directly. Thanks for watching. We'll see you all next time.